welcome to this afternoon's PyCon session for Saturday. I'd like you all to make Chris welcome, talking about guardrails.
Thank you, Paul. Welcome to my talk. As Paul said, it's called Guardrails, and before I begin, I want to mention that some of my early slides include blurry photos of non-severe incidents in historical motor races. If you want to look away for a bit, I'll let you know when you can pay attention again. But otherwise, let's get going. This is a talk about how we choose to structure our programs, about how we communicate the structure of programs and libraries to others. It's called Guardrails. I also want to warn that this talk is conceptual. You're going to need to think about how to put what I'm talking about into practice. This is not a very practical talk. I'm sorry about that. I really am. So let's get started. Before we talk about Python, I want to talk about Formula One and its difficulties with the C. In 1928, the National Automobile Club of Monaco, that's this tiny country marked out here by the yellow line, became involved in a regulatory dispute. Despite running the very successful Monte Carlo rally in the nearby French hills, the club's effort to be recognized as a national body by the international motor racing fraternity of the time was disputed by the French on the basis that Monaco did not itself host any motor racing events and instead ran all of its own events in France, which, as you know, is a different country. The Monaco club immediately sought to rectify this, not letting the country's area of barely 2 square kilometers get in the way. They picked the 2 widest roads in the city as the basis for a racetrack and started holding the Monaco Grand Prix. The problem is that those 2 streets were directly next to the harbour. The first event in 1929 was wildly successful, so they kept running it and rerunning it. This photo is from the 1931 event, and you can see the logistical challenges here. On the left, there are some trees, and the harbour is on the right. This is not a terribly sensible location for cars to be driving very fast, but they needed to run this race on these streets so that they could have control over the rally, which is the race that they actually cared about. Now, as you can see up the back here, that's a hill with a corner and a significant couple of direction changes that lead straight onto the Harbourside Straight. There is a braking zone and a turn that would leave you pointed at the harbour unless you recovered and pointed back towards the racetrack. So back to the track. See on the right here, the track limits. The only thing keeping you out of the water were some sandbags and some iron ship moorings. An incident was only a matter of time. In 1955, Alberto Ascari misjudged his travel down the hill and only managed the first of the 2 direction changes and flew straight into the harbour. Thankfully, Ascari was thrown from his car, seatbelts not being a thing at the time, and swam to shore. Australian driver Paul Hawkins managed the same thing in 1965, somehow going over the top of the edge of the circuit, now marked with hay bales instead of sandbags, much safer. But clearly something needed to change. Hay bales were not enough, and solutions like portable concrete barriers, though good for stopping cars from going over the edge, had other undesirable side effects. The solution came in the form of the steel traffic guardrail, marketed at the time by the Armco Steel Company of Southern Ohio. The W-shaped cross-section absorbs head-on impacts directly and slowly, and by bolting spans together, impacts can be absorbed over a significant distance, reducing the travel of the barrier at the point of impact, making it far more likely that the car and the driver would remain within the bounds of the circuit. By 1971, much of the circuit was surrounded by these Armco barriers. And while that section at the bottom of the hill remains a hotspot of incidents, there hasn't been an incursion into the water since 1966. And that's the end of the photos that you'll be seeing in this. So if you were looking away, you can stop looking away now. So beyond safety, the presence of Armco barriers had some significant side benefits. By being as tall as the cars, they gave visual indicators of where the track limits were, allowing drivers to brake far more precisely. Races and cars adapted, and within the decade, speeds at Monaco existed the pre-Armco days. Barriers also greatly reduced the scope of incidents on the racetrack. Cars would now remain within the confines of the track. And this predictability means that today, marshals can clean up after most accidents in a handful of minutes. And thanks to their deployment in racetracks, today Armco barriers are used throughout the world as a way to reliably stop people from driving off the road in otherwise dangerous places. And now that's enough talk about race cars and the problems they have with the sea. And now let's talk about programming and the problems that we have with the sea. C, more than any other programming language before or since, has shaped how we think about writing software, and that's not without its consequences. C is a deliberately very small language, and most of the features in the language roughly corresponded to the features of one specific CPU. And the remaining features were built around code organization so that you could keep your programs in your head. And this stood in stark contrast to other languages at the time that were not focused on the computer's capabilities, but rather the domain. You can think of COBOL, which was for business applications, or Fortran, which is for scientific processing. Now, access to the full capability of your computer was great, but being able to do anything with your CPU means being able to do anything with your CPU, including the things that are undesirable. It's easy to make something that doesn't work entirely as intended. This is some very reasonable code, but it can easily access memory that it's not allowed to, and your program will die. You actually have to think about what your program is doing in order to avoid an error that stops execution. So all too often, the intent of code gets obscured by defensive error handling. Or to put it another way, the act of understanding the effects of a program or how to use a language or library effectively is not the same act as writing code itself. It's not trivial to use a function in a C library without reading the documentation for that specific function. And this might sound flippant, like we should definitely read documentation. Documentation is good. But documentation has to convey all sorts of minutiae that get in the way of thinking about what your program does. The consequences of not deeply understanding the contract of a function in C are worn by you, and they can frequently be unpredictable. And the first generation or two of languages after C sought to solve incremental problems beyond C. Better code organization, better portability, better text processing, no need to compile, better data structures. But each of these languages, certainly in their early days, were still geared towards that same philosophy of programming. Your code has a universe of effects, and it's up to you to make sure that your program doesn't touch dangerous or broken situations. So take this two-lined piece of Python code, for instance. In these 2 lines, I can count at least 2 potential error scenarios. What if example.com times out when you try to connect to it? What if this URL doesn't return a valid JSON object? And this code runs just fine on the happy path, but it's up to you as the programmer to infer where errors might occur and program defensively around that. And so you can handle it with a blunt instrument, but this is really no better than the first case, other than you get to write your own error message. Okay? The alternative is that you can start scoping your exception blocks tightly to each error point, and that itself gets to be tedious. In Python, your options are to either be permissive and let your routine explode, or you can be exceptionally defensive and handle every possible error scenario. Now, if you care about your programs not throwing exceptions, you should be doing the latter, but the tools that we've grown to use in Python require us to predict where exceptions are going to occur and to fortify that code. And that's what it means to work safely in Python. This is producing code that doesn't blow up, end unexpectedly, or have unpredictable behavior. And it's where we as programmers have to do the work to ensure that our programs behave correctly. And then we have to do work to communicate how our programs work correctly. Or to put another way, we have to document what our program does and how to make it do what it should do. And then we need to test things to make sure that they actually do the right thing. And neither of these things in isolation are bad, but without appropriate tools, they are incomplete and insufficient. So the general approach to testing is that you write a bunch of cases, and each case represents a fraction of the code paths that your program could take. And we definitely have tools that can tell us about how much of our code base was exercised under test conditions. That's what code coverage is. But this approach to testing is invariably reactive. Even if you follow test-driven development, if you notice an error condition after the fact, you still need to patch it up with other tests because you haven't considered the full scope of bad behavior. And code coverage is only a useful metric across your own code base. It does not tell you anything useful about how your dependencies are going to interact with your code. Making a test suite that covers 100% of their code paths that your code itself can exercise is basically an act in futility. Do you know every place that every library that you use will throw an exception? This is just not something that Python is particularly good at communicating, and it makes guaranteeing that our code is safe a process of guessing. And because most Python code does not communicate its structure completely, this means that instead of documentation that can focus on use cases and intent, you must explain the shape of your library or program before you can explain how it works. But this documentation is decoupled because the act of explaining how to program is separate from the act of programming itself. If a program evolves, but the documentation does not, then users aren't going to be able to figure out the structure of your program, let alone how to interact with it properly. And most failure cases for documentation are not these structural failures, are these structural failures, rather than misdocumentation within a correct structure, which is a far easier problem to fix. So this is ineffective. The normal way of programming is that structure is communicated implicitly, and the only foolproof way of determining that structure is by interacting with it. Because when the structure is not revealed directly, discovery is inherently a process of trial and error. Communicating structure and interacting with that structure should not be separate acts. What we need are tools that communicate structure for us, make it clear where the safe places to work are, and leave errors predictable. What we need are guardrails. So what do guardrails for computer programs look like? Well, it turns out they look like the same as the guardrails I talked about earlier. They use structure to show you what's guaranteed to be safe. They limit the range of undesirable consequences, and in doing so, they make it easier to reason about possibilities. In short, guardrails are features that use structure to show you what is possible and what isn't, and in doing so, they guide you towards more correct programs, often by letting computers figure out automatically whether we're entering unsafe territory and ruling those spots out. So over the last 2 decades or so, rather than adding features to let you take advantage of new things that Python couldn't let you do before, Python has steadily introduced guardrails as first-class features in the language. These are tools that help us interact with Python better and communicate our intent to others better and avoid undesirable side effects. So let's look at 3 features of Python you may already be familiar with and explain how these features serve as guardrails. So the with statement is the first guardrail that I want to explore. And to explore that, we need to look at the risky behavior that it replaced. So with statements are used to handle resources that need to be acquired or released, things like locks, file handles, or sockets. It's actually really hard to get the life cycle of objects like files correct. So say you open a file handle, you write to that handle and then close the handle. If that works well, everything is absolutely fine. But what if it doesn't go okay and you can't write to the file? Well, then you get an I/O error and your program explodes. This is where things start to get difficult. So if you need to handle an error, do you put it outside the try except block? Well, this is very good unless you want to propagate that I/O error up your call stack. You might prefer to put another handle.close inside the except block, which is slightly more correct. But as you can see, it's starting to demand a lot of the developer to get this exactly right. You need to duplicate a lot of code. And this is why we have try except finally. Whatever's in that finally clause, if you haven't seen this constructor before, that finally clause, that will get run when you leave the try block. And this is great for making sure that resources are all cleaned up properly when you're done with them. But there are several problems with this. The first is that you need to have heard of try finally before you can use it. It's difficult to read, like does the accept block get handled before or after finally? And also you can code with try and accept or even without try at all, and you'll have something that works on the happy path, it looks complete, but it has subtle bugs in it. Basically, it's a trivial feature of Python, but incorrect usage is more accessible than correct usage. So this is likely going to be a source of bugs. So we got the with statement instead. The handle for a resource is valid when you enter the with block, and it becomes invalid as you leave the with block. You get a visual reference to where it's safe to work with the handle and where it isn't. So the with statement is a guardrail. It uses structure to show you the life cycle of a resource. It builds correct error handling into the structure of the code itself, so that even if you don't do any error handling yourself, the resource is managed correctly. And it even makes it easier to reason about where to put your exception handling. If you need to access the file handle in your exception handling, you put it inside you put the try except block inside the with block. And if you don't, you just put it the other way around. And it actually becomes easier to reason about execution order. Because Python is showing you how to use its feature, it's easier to write code that gets it right the first time than it is stumbling into correct behavior through trial and error. So the with statement is a guardrail. And it's a guardrail that you can build into your own code quite easily. You can look up the docs for contextlib.contextmanager to see how to do this. It's really very simple. So the second thing I'm going to talk about are async functions, which are interesting because they're an example of a way to introduce guardrails for a piece of machinery that already exists in the language in its entirety. So async functions can only be called in an async context, an event loop or something like that. The async await syntax gives you tools to make sure that you're using async await in the correct way. You can only await a thing if you're in an async function. This both makes it clear that you need to use async functions together with other async functions, but also it gives you some structural indication of where you're yielding control back to the event loop. And this compares really favorably to what you got before the async syntax, which was to make use of the existing generator syntax and this yield from construct. It's not immediately obvious to someone without access to source code that this function here is asynchronous. But it is, you can trust me on that. To effectively describe something as asynchronous, previously you either had to provide docs that pointed out that something was a coroutine, or you could use names, or you could do here what I did, which is both. And there's no language level barriers that prevent you from accidentally awaiting something that isn't itself awaitable in the same way. Like this. Async await gives you both a convenient programming construct that lets you communicate that you're doing things asynchronously, but it's also one that lets Python verify that what you're doing actually makes sense. Now, guardrails don't just show you spaces that are explicitly safe. They also make it clear where things are not safe. Decorators show you a piece of syntax that's normally straightforward to understand is about to be subverted, and that you need to make extra effort to understand what's going on. They highlight places of risk rather than the lack of risk. And decorators exist because Python lacked features like class methods or static methods that other languages have. But it was possible to implement them at runtime. But to do that, you would need to define a method, and then after defining the method, you would assign the decorated method back to its original name. And there's a lot to hate about this particular pattern. You're changing the semantics of a feature of a language at runtime, but that feature that you're doing here, it's genuinely useful. Like, we do this all the time. What's particularly bad here is that the confusing thing happens out of sight of where you're defining something that looks like it should be behaving normally. And if your method is really long, it can be difficult to somebody reading your code to notice that this decoration thing is happening when they skim through the code. So by having the decorate syntax in Python available, it means you can put the thing that's potentially confusing up front where people are skimming through things. And it makes it more obvious to people reading your code what is going on. But in and of themselves, decorators still don't tell you what's being changed, just that something is going to be changed. If you're writing your own decorators, it's still not immediately obvious whether your decorator is going to return a similar function or whether you're going to modify things further. And this is where another of Python's guardrails can come in. You can use static type hints to communicate structure in a way that will be communicated to people who read your code. If you have a decorated thing that's going to behave broadly similarly to the function that you've originally written, you can use bounded type vars to show that. But if you're going to do something completely unexpected, you can also show that with type hints. So Python has been evolving as a language. It's gone from being a C-style open field where all the possibilities are open to you, and it's up to you to figure out whether something is right or wrong just by playing around with it, to a language with constructs that show you how to safely use them and to highlight risks or unexpected behaviors where they occur. But there's still a lot of historical baggage in the language, and you have to coexist with that historical baggage. You can build your own guardrails into interfaces that you develop, and you can experiment with other people's interfaces by using defensive coding techniques based on those guardrails as well. So you've probably seen an example that looks like this when you're learning Python, or something that looks very, very similar to that. Like, what happens when you make a list, you assign that list to another variable, and then you're going to amend that second list. So the answer is that because Python treats variables as references to objects, a list and another list actually point to the same object, so you're modifying the same object under the hood. This is true of Python's built-in data structures. It's true for your own classes. And because you're an experienced Python developer, you know how to avoid this in your own code. But what happens when you import someone else's function and pass your list into that? Well, at that point, you're trusting that the implementer does what they're saying they will and that nothing unexpected is going to happen. And much of the time that works out, particularly if you have good tests against that library. But what if you want more guarantees? Consider using immutable data structures. If you're working with lists, pass a tuple instead. If you've got a set, pass a frozen set instead. If you've got a dictionary, I can't help you. Key value pairs in a set, maybe. Or you can rewrite it as a concrete class using frozen data classes, which is what I tend to do instead of using arbitrary dictionaries everywhere. All of these structures that I've spoken about enforce immutability at runtime. So by passing in those sorts of structures to other people's functions, you'll discover through errors being raised everywhere that they're making changes and you need to protect against that. Through experimentation, at the very least, you can discover if you need to copy things or plan for contingencies. If you're writing your own interfaces, though, you can tell people that you're not going to be changing things. Static typing and type hints is a really powerful guardrail. You can directly express to your consumers exactly what operations you're willing to perform on an object and let them make their own decisions about how to use your library. So if you're dealing with standard data structures in Python, there are abstracts in the typing module that cover immutable and mutable versions of these without depending on a particular structure type. But what if you've got a class of your own? Recent versions of Python support structural subtyping in the same way that Go supports structural subtyping, if you've seen that, through a thing called protocols. So if you have a class that has an interface like this, you can write a protocol interface that describes the things that your function is going to work with, and then your type checker can verify that a class that you've written matches, that the protocol matches. More importantly, it can do this for classes that you did not write, written in contexts that weren't aware of how you chose to define types. And this is great, but this example doesn't help with immutability, but you can fix that as well. You can just use @properties in your protocol, and that makes the type checker verify that you aren't writing to that attribute. With protocols, you can make your contract with your code's consumers explicit. You can show them exactly what parts of the interface you're going to use and what you're going to do with them, and you can automatically verify that your side of the contract is fulfilled, and you give your consumers a clear idea of what it is that they need to test in their own tests. And the last idea I want to touch on is the big one. I brought this up at the start, expressing and handling error states, because this is what working safely is really about. It's making code that doesn't fail randomly because you failed to predict that a certain library is going to throw an exception, which is difficult because Python's most obvious tool for handling errors is the exception, and it's not really a very good one. Exceptions interrupt the flow of code. Handling them efficiently is not particularly easy, and for the purposes of this talk, it's unpredictable when and where they can occur. They're meant for exceptional circumstances that need special handling, but Python just uses them everywhere for most errors. Now, this unpredictability around exceptions, it's not a new thing. Java has had its own guardrail for handling exceptions since the early days, a thing called checked exceptions. If a method says that it can throw a particular sort of exception, somewhere in the call chain has to say that it catches that exception. And this sounds great until you have to catch 6 or 7 different types of exception, and then your code tends to be more exception handling than it is actual functionality. And if you're dealing with a situation where an error state is actually part of the normal and predictable flow of your code, then you have 2 choices here. You either have to code defensively by using if guards or try guards. You litter your code with exception handling, basically. And actually, this makes us complacent as to when errors are actually likely to occur. It is much easier to ignore it. And I've lost track of the number of times that I've let code that effectively lets an obvious exception opportunity into prod because it was much, much easier for me to just send it into prod than remembering that a value error might get raised by something or whatever. And so a trick that's popular in functional languages and more recently in Rust is to use result types as return values from functions that may have errors. The basic idea is that a function can either return a success or a failure value, and your code has to acknowledge that before you can read the success value. In Python, you can do this with union types from the typing module. And so if you want to write code quickly and you can tolerate an exception, well, you just assert that it's not the particular type that's wrong. Or you can use conditionals to handle it like a variable. And that's it. Like the type annotation here shows you that there's an error condition to handle, and you know how to handle that error. And more importantly, the type checker also understands that there is an error condition to handle and that your code won't pass type checking until you write code that acknowledges the possibility of there being an error. And this gives you so many more guarantees than you'd get if you solely used exceptions. And this approach also lets you reserve exceptions for cases where it truly doesn't make sense to continue on. Both immutability and result types do a couple of things to how you work safely with each other's code. The first is that by conveying structure in code that you can read and a computer can verify, there's less need for documentation to explain edge cases. If a function won't mutate an argument, you no longer have to explain that. If a function can return an error as a return value, then that can automatically be verified, and so you don't need to explain in your documentation that an exception can possibly occur. And being able to verify that you're handling all possible output cases from a library means that you can actually trust that code coverage is giving you a useful metric when you're interacting with a particular library. And so that's a selection of 5 examples of guardrails. These are all examples of using programming constructs to convey the structure of functions to the people who call them so that you can understand what to test and focus on documentation to give tactical understanding rather than merely explaining structure. And these examples show that Python cares about using structure to communicate how code works. New language features are, more often than not, features that give humans better ways to manage the structure of their code rather than simply expanding to allow all of the features that our computer has. And sometimes these are duplicated features. The first way to do something might be to enable that behavior at all. Think try finally or yield from, but really they're features that are there should you happen upon them. Context managers or async await actually show you how to use them so that it's clear from reading code that you're using them correctly. And that's how you should be thinking about selecting which Python features to use. Python gives us guardrails and gives us tools to make our own so that we can spend less time understanding the space that we can work in and instead actually doing the work that we want to do. And just as Python gives us the tools to work more safely, we ourselves can structure code so that other people who interact with our code can understand the assumptions that are baked into our code just by looking at the structure that we expose, allowing them to write safer code with more focused tests. So yes, testing is still important, but having verifiable structure tell you what is possible and what isn't means that you don't have to write as many tests. If there's no chance of an exception popping up, then you don't need to test for exceptions. And so documentation can, rather than describing the structure of a function, focus on the why and the how of a function. Documentation still needs to exist, but the focus no longer needs to be on the things a computer can understand for you. Your documentation can become tactical or communicate intent instead. The signs are that in most cases, we've outgrown languages or frameworks that merely expose the capabilities of our computers and trust us to understand the structure that we need to put in place to handle those capabilities. Instead, languages give us constructs that let us use computers safely, and those are starting to take hold. Python, it's a language that emerged in the shadow of C, but has stayed relevant for 30 years, gives you both options. So you can do whatever you want and wear the risk of unpredictable errors, or you can use guardrails. Thank you.